Hello, I'm Dr. Erica Salazar, a Magnet Systems Lead at Commonwealth Fusion Systems. It's Friday, the 11th of March. Before we dive into this week's fusion news, I would like to first acknowledge and condemn the Russian invasion of Ukraine. My heart and thoughts go to the Ukrainian people during these hard times, and while many have it worse, fusion research is not immune. The Kharkov Institute for Physics and Technology is a member of the Eurofusion Research Consortium, and it has been reported that Russian rockets have struck their facility. We wish the best to our colleagues in Ukraine. And now, here are the headlines this week. 1. Researchers examined the performance of a fusion pilot plant to generate electricity. 2. Self-sustained divertor oscillation mechanism identified in fusion plasma experiment. 3. Innovative new magnet could facilitate development of fusion and medical devices. 4. Energy Singularity completes financing led by MiHoYo and Neo Capital. And I've got a few bonuses at the end. 1. Researchers examined the performance of a fusion pilot plant to generate electricity. Back in 2020, the Fusion Energy Sciences Advisory Committee published a report titled Power the Future: Fusion and Plasmas. Based on the recommendations of this report, the U.S. fusion community is calling for immediate design efforts of a cost-effective fusion pilot plant to generate electricity by the 2040s. Dr. John Menard, the Deputy Director for Research at the U.S. Department of Energy's Princeton Plasma Physics Laboratory, led a study discussing the scientific and engineering challenges a fusion pilot plant will face. With these challenges in mind, Dr. Menard suggests the development of a complementary research facility to close these gaps. In order to fully address the challenges of a pilot plant, the proposed research facility would also build a smaller tokamak device named the Exhaust and Confinement Integration Tokamak Experiment, or EXCITE for short. The EXCITE tokamak device will be designed to complement and inform the pilot plant, where it would serve as a satellite to test ideas during the pilot plant's construction and operation. Dr. Menard believes a relevant example is how JET, the Joint European Torus, implemented a metallic ITER-like wall a decade ago in order to gain knowledge for ITER operation. And as our viewers may know, JET recently broke some amazing fusion energy records using this ITER-like wall. And if you didn't hear about it, make sure to check out Sid and Omri's recent Fusion News videos. 2. Self-sustained divertor oscillation mechanism identified in fusion plasma experiment. The divertor is a very important component to any tokamak device. It's often considered the waste removal system of a tokamak during operation. Tokamak designs aiming for higher energy outputs and higher density plasmas require more efficient diverters to remove heat and plasma impurities. Higher plasma performance requirements are driving higher diverter heat load requirements, and conventional diverter designs are having trouble keeping up. Research by Tatsuya Kobayashi aims at reducing the plasma heat load to the diverter while maintaining the core plasma performance. Researchers alleviate heat loads by applying external magnetic field perturbations which cause plasma detachment at the diverter. These conditions have been experimentally proven to reduce heat loads, but the background physics was not fully understood until Kobayashi and his colleagues successfully reproduced the experimental observations by applying what is called a predator-prey model to the electromagnetic physics of the diverter. This model explains the oscillatory and competitive behavior between the magnetic islands, which reduce the plasma heat loads, and the plasma current, which is induced in the diverter. Kobayashi states, "Through this work, we significantly deepen the understanding of the background physics of the diverter detachment operation. Next, we plan to develop a stable and efficient detachment scenario, utilizing the background physics knowledge obtained through this work to realize the magnetic plasma fusion plant." 3. Innovative new magnet could facilitate development of fusion and medical devices. Scientists at the Princeton Plasma Physics Laboratory, or PPPL, have designed a new type of superconducting magnet with potential to boost the high-field industries, from magnetically confined fusion devices such as tokamaks to medical devices such as MRIs used to scan the human body. As our viewers may know, magnets are crucial to the stability and performance of the plasma in magnetic confinement fusion devices, such as a tokamak. More and more research projects and companies, such as Tokamak Energy and Commonwealth Fusion Systems, are focusing on innovative superconducting magnets to boost fusion device performance. Scientists at PPPL are looking at high stored energy magnets made out of niobium-310, a low-temperature superconducting material also used in ITER magnets, but without electrical insulation. As stated in their published paper, qualification of conductor insulation is one of the most challenging but critical issues in manufacturing of fusion magnets. Additionally, the organic materials used in conventional insulation systems degrade at a much lower neutron fluence level compared to the rest of the magnet. And as we begin designing fusion power plants with long-term, sustained operation, the design of a magnet able to withstand long-term neutron fluence will be key. This team of researchers are designing and testing various different insulation methods, including the use of metal as an insulation. Now, compared to a superconductor, which has nearly zero resistance, a metal such as steel has significantly higher resistance and can act as an insulator. A downside to using a magnet without any turn insulation is that it will take a very long time to charge up to full current or magnetic field. This may not be an option for the central solenoid of a tokamak, but it could easily be used for the toroidal field magnets of a tokamak and the magnets of a stellarator, since they do not require rapid ramping of their magnets. The magnet research team have built a prototype magnet and demonstrated encouraging results. PPPL Chief Engineer Robert Ellis says, "This new concept is interesting because it allows the magnet to carry a lot of electrical current in a little space, reducing the amount of volume the magnet occupies in a tokamak. This magnet could also operate at higher current densities and stronger magnetic fields than magnets can today. Both qualities are important and could lead to lower costs." 4. Energy Singularity completes financing led by MiHoYo and Neo Capital. Energy Singularity is a fusion technology company based in Shanghai, China. Founded by scientists and physicists ranging from Stanford and Princeton University in the US to Peking, Tsinghua, and Shanghai Jiaotong University in China. Energy Singularity's mission is to explore the commercialization of fusion energy technology. They are currently aiming at providing components and services for the development of the experimental advanced superconducting tokamak, also called the EAST tokamak. Recently, Energy Singularity completed its first round of funding, up to a total of $63 million. MiHoYo and Neo Capital led the funding round, followed by Sequoia, China's seed fund, and Blue Run Ventures. Now, some of our viewers may have heard of MiHoYo, the maker of Genshin Impact, a very popular online game. News about MiHoYo's investment in fusion energy has spread across the gaming world as well. For example, there's an article published in PC Gamer titled "MiHoYo's Spending That Genshin Cash on an Experimental Fusion Reactor," and IGN's article, "Why Genshin Impact Developer MiHoYo is Investing in Fusion Energy." They both describe why a game creator wants to invest in fusion. A combination of the game's huge success, making over $2 billion in its first year, and the company's motto, "Tech Otakas Save the World," are all part of MiHoYo's motivation behind the investment of scientific projects such as fusion energy that aim to make a large impact on our world. And now I have some bonuses for you at the end. White House Summit, developing a bold decadal vision for commercial fusion energy. The White House Office of Science and Technology Policy and the U.S. Department of Energy will host a live summit on developing a bold decadal vision for commercial fusion energy on March 17th. This summit will host government leaders, policymakers, scientists, investors, stakeholders, and private industry to build a plan for American leadership in the commercial fusion energy space. This is a very exciting future event. Check out the FIA website or the links in the video below to find out more details how to stream or watch the summit live. Selecting the right structural materials for fusion reactors. This article discusses the recent corrosion research on breeding blanket material of fusion power plants. The breeding blanket is typically made up of a lithium alloy that surrounds the plasma core. It acts like a blanket that absorbs the neutrons and heat from the plasma fusion reaction and breeds tritium in the process, which is a fuel for the deuterium-tritium fusion reaction. This article describes the ongoing corrosion research between certain breeding blanket materials such as lithium lead with structural materials such as silicon carbides. Check out the links below for more information. Nuclear fusion. How excited should we be? The exciting results about JET's recent fusion energy records have been all over the fusion energy news lately. This short article does a great job describing why the JET results are a landmark milestone towards the development of fusion energy and the challenges that remain. If you're interested in checking out a short and concise article about JET's recent results and how it fits into the bigger picture, give this article a read. Well, that's all for your fusion news this week. Please subscribe to our channel and check out the links in the description below for more information. Until next time, bye.